So let's introduce our speaker tonight, and what a resume. Just shocking. Thank you, Franco, for finding her and making this happen. But Brett Denevi, she's a principal staff scientist at the Johns Hopkins University Applied Physics Laboratory, and her research focuses on the origin and evolution of planetary surfaces, particularly the history of volcanism, the effects of impact cratering, and space weathering. She's been a member of just a ton of NASA mission teams, including 4 ongoing or upcoming missions to the Moon, Deputy Principal Investigator of the Lunar Reconnaissance Orbiter Camera, co-investigator on NASA's ShadowCam instrument on the KARI Danuri orbiter, and co-investigator on the Lunar Vertex and Lunar-VISE, which is going to be landing on the Moon in 2024 and 2026. So she's also served on the steering group of the recent Planetary Science and Astrobiology Decadal survey, and as vice chair for the panel on the Moon and Mercury. She is the science chair of NASA's Lunar Exploration Analysis Group and is the recipient of a NASA Early Career Fellowship, 7 NASA Group Achievement Awards, and just to top it all off, she had an asteroid named after her too. So, I mean, that's a pretty good resume, I'd say. So won't you please welcome Dr. Brett Denevi. Thank you, Doctor, for joining us today. Thank you.
Oh, thank you so much. It is so great to be here. And I'm going to start sharing here, but it was a real treat to get to see those photos you were sharing earlier. Wow. I just sit at my computer and take pictures. Okay, so hopefully I'm just going to make sure you can see the slides okay and hear me okay. Yes. All right, awesome. Okay, so I'm going to talk a bit about just what's going on at the Moon these days, because there is a lot. And happy to take questions throughout or at the end, however you prefer. So I assume, being astronomically inclined, many of you watched the launch of the SLS, but I think for many people in the lunar science and exploration community, this is kind of the real start of a new era here. So this was just about a month ago. The SLS launching with the Artemis 1 mission. This was 3 weeks ago. You can see the Moon and Earth behind the Orion capsule. This was from one of the closer orbits to the Moon. This is just north of the Aristarchus Plateau, seeing these beautiful basaltic plains. And then with the splashdown, the successful completion of the Artemis 1, the uncrewed test mission, we really are on the precipice of a new era here. The last US robotic lander, I think really shockingly, was Surveyor 7 in 1968. So this is a view near Tycho crater. I'm just gonna minimize the pictures there. This is a view near Tycho crater. You can see, this is very old Vidicon technology, but landing in a really spectacular site. And then, of course, the last crewed landing was in 1972. That mission splashed down 50 years ago yesterday, which has often been kind of a sad anniversary in some ways, because it's been a reminder of how long it's been since we have been back to the Moon. And I often, when I talk to school kids, I ask them how long they think it's been since people have been on the Moon, and they answer, yesterday, last week. I'm like, no, it's, since before your parents were born. But now in the next 3 years, the United States has 13 landers planned. That includes, the SpaceX, their uncrewed demo. That includes multiple robotic landers, and then the Artemis 3 lander. So we'll see if those all really happen in the next 3 years. But the fact that there are so many on the books, and some will be happening in those 3 years, is pretty spectacular turnaround here. And then, of course, there'll be some new orbital investigations joining the fleet at the Moon. And then international exploration, by far the biggest international exploration program is coming from China. They've already had 3 landers, including a sample return, but Japan, India, Europe, there's a big international push. So where is this all coming from? It's not out of the blue, but a lot of this new push started with Space Policy Directive 1. That was what came out in 2017. And that space policy stated that the US will lead an innovative and sustainable program of exploration, including the return of humans to the moon for long-term exploration and utilization, followed by human missions to Mars and other destinations. And then I've included a second quote here. More recently, the Artemis program will establish the first space station in lunar orbit and the first lunar base camp where astronauts will train for the first missions to Mars. And that's from our current vice president, which is notable because this Artemis program has survived 2 administrations, which is a big step for a deep space exploration program. So I'm including a lot of words here. I promise the rest of the slides won't have as many. But what is sustainable? Oh, and we need to pause 1 second for a hug from my daughter. Okay. All right.
I want you to pause all the time for that.
All right.
Always pause for that, please.
The highlight of the presentation.
Yeah, that's great.
All right. So the sustainable part was what was in Space Policy Directive 1, and that is an important component of this because that is what is really different this time around from Apollo. They've included, there's various definitions of sustainable. To some people it means reusing infrastructure. It means having a long duration presence on the moon. But I like this definition of sustainable. We provide our working definition of sustainable as meaning there are widely accepted reasons to continue human lunar exploration that justify the continued investment, commitment, and risk beyond a few missions. And the reasons to continue the lunar program include ongoing scientific discoveries, investing in potential commercial development, technology development, educating the next generation of STEM professionals and a scientifically literate public, and inspiring the public about our individual and collective opportunities and future. And I think it's really important to remember that second part there. Why are we doing this? Why is it important? And a lot of what I'm going to talk about tonight is really what we're going to be learning. What are the important scientific discoveries that are going to come out of this era of lunar exploration, and a bit about what's going on in terms of the potential commercial development. These words come from the most recent Decadal survey for planetary science and astrobiology. So I think this is a really cool thing that NASA does. Every 10 years, the different fields in planetary science get together. They ask the national academies to do a consensus study of what should we be doing? What are the most important scientific questions in this field? And how are we going to address them in the next 10 years? So I worked on this for the Origins, Worlds, and Life report that is trying to set the path for the next 10 years, particularly for the moon. And so from that came these science themes for lunar exploration. They get at really the kind of the fundamentals of what's important, and not just to lunar scientists, but what is important to the entire field, because the moon can teach us a lot about solar system in general. And so I'm going to talk about 2 of these 3 themes. It's funny because I love geologic processes. The moon has a lot of volcanism, but tonight I'm going to focus on solar system history and the water and volatiles and what we're hoping to do. What are the big open questions there? And so as you see here, and as you saw from some of those really beautiful pictures that we saw earlier in the evening, the moon is heavily cratered. And that is one of the most important things that it can offer planetary science, because that record of cratering spans almost the entirety of lunar and solar system history. It's giving us a peek back into what was going on at the Earth-Moon system 4.5 billion years ago. And I'm highlighting in orange here now every crater on the moon that has been mapped that's larger than 5 kilometers. So you can see there's a huge range of sizes and densities too, which are telling you that some of these areas are younger than others. But if you look at just the incredible density of impact craters here, and now you contrast this with the Earth, this is really getting at what is so important about the moon. Over here, you can see impact craters that have been mapped out on the Earth. There's really only a handful of these. And I should note that these circles are vastly exaggerating what their actual diameter is. The largest terrestrial impact crater that is known is about 200 kilometers in diameter. And of course, all of the things that make Earth a really great place to be are also the things that make it a terrible preserver of its own geologic history. You can see a couple really great terrestrial impact craters that are known in Canada. And these just really erode very quickly due to wind, water, plate tectonics, life. This is one of the most famous impact craters down here in the lower right. This is the RISE impact crater. It's in Nordlingen, Germany, and it's about 24 kilometers in diameter. This is a picture that I took inside the crater on a geology field trip to study this crater. Isn't it spectacular? It looks just like an impact crater there. It formed 14 million years ago, which is, that's actually really recent in terms of geologic history, but it's already been so severely eroded. And now we contrast that with the moon. This is inside the Tycho impact crater. Another picture I helped to take, although remotely. And so Tycho is 80 kilometers in diameter, and it formed well longer ago, 110 million years ago. This was long enough ago that if the dinosaurs had looked up, they could have gotten a preview of their fate, would have seen a spectacular sight on the moon's near side. But this, again, is really getting at what is just so amazing about the moon. This crater is 110 million years old, and yet you can see its features are so well preserved. It looks like they formed yesterday. The central peak here inside of Tycho crater, this formed because the asteroid or comet was traveling at over 10 kilometers per second. It hit the moon with such force that the ground was pushed down, compacted, and then rebounded up to form this 2-kilometer tall mountain in just a matter of a couple of seconds. Zooming, well, first I'll note too, this surroundings here are molten rock. They're a sea of molten rock that melted during the impact event and now is frozen in place here. Great place to sample and date this crater. Zooming in just to show you incredible details. This is one of our most famous images, and the details are just so beautiful. This rock here in the center on top of the peak is about the size of a football field. So these younger craters, I mean, there's a lot that they can teach us about the impact cratering process, about the more recent impact flux in the solar system. But really kind of the key question is getting back to the ancient history, because that is what's preserved so well on the moon and is entirely lost on Earth. So this big crater here, this is the Imbrium Basin. It's over 1,000 kilometers in diameter, and it formed 3.84 billion years ago. And we know that age because we have been there. This crater or basin has been dated from multiple landing sites, actually. But here's an example. This is from the Apollo 14 landing site, which landed on the Frau Morau formation. It's been mapped as the impact ejecta deposit of that Imbrium impact event. And so the Apollo 14 astronauts, out of this field of boulders here near Cone Crater, returned this sample 14051. There is that rock on the lunar surface. And then here's that rock in the lab. And this is a rock that was melted by the impact event. Its radiometric clock was reset, and dating that gives us that 3.84 billion year age for that impact event. And if you look at in yellow here, these are the various Apollo landing sites. Here, these are the 3 Luna Soviet robotic sample return sites. There was actually one more. I need to update this. Chang'e 5 returned samples from from Oceanus Procellarum over here, a young basalt. But because we're focusing on the ancient impact events, we'll focus here on Imbrium Basin, which has been dated from these Apollo samples at 3.84 billion years. We also have Serenitatis, 3.89, Chrysium, 3.89, and Nectaris at 3.9 billion years old. And the astute observer will note that these ages are very close in time. They're all right about 3.9 billion years old. And this is actually pretty late in the solar system history to have these very large impact events. We think that most of the leftovers of planetary accretion were really swept up very quickly after the planets formed. And so this is almost 600 million years later, and we have these huge impact events. And so this has come to be known as the late heavy bombardment, because it is very long ago, but still later than you would think it would be. And so this is a kind of sketch of what that late heavy bombardment looks like. It's also known as the lunar cataclysm. We have the age. This only goes out to 3.6 billion years, but this is that very rapidly declining early flux, and then just this spike at 3.9 billion years in the impactor flux. And there are various models. At first, this was really just confounding and hard to explain, but there are various models that have now been conceived and that actually do a good job of explaining why you would get this huge bombardment. This is one of them. This animation is going to loop through a few times here, and I'll take a moment to explain it. But this is the Nice model because it was formed by some people in Nice. There's the Nice 2.0, there's the Grand Tack, there's giant planet migration, but they're all kind of variations on a theme and really vary only in for our purposes, the details. So what we're looking at here in red is the orbit of Jupiter. In orange, Saturn. In blue is Neptune. And then in purple is Uranus. And all of these green dots are icy planetesimals that were stable for some time hanging out in the Kuiper belt. And according to this model, these various models, what happened is everything was fine for a little while. You can see time ticking by, time since the, I don't know, beginning of the solar system or very slightly after. And Jupiter's orbit Jupiter got into a mean motion resonance with Saturn. This caused the orbit of Neptune, which had been way in here, to really swing outwards. And Neptune just kind of careened through the Kuiper belt like a wrecking ball, sending these icy planetesimals scattering. And so according to these dynamical models, the lunar cataclysm was really just a part of a total solar system-wide late heavy bombardment, because these planetesimals, icy objects, were being just totally scattered throughout the solar system. And this has all kinds of implications. This is an artist's depiction of early Earth. 3.9 billion years is an important date to the early Earth, because we think that life was beginning to form right about that time. So understanding the Earth's habitable environment at that time is really kind of key. You know, how did life form? Did it have to form multiple times because of this crazy bombardment? If you had impact events like Imbrium, like Serenitatis, like Crisium, those are large enough that they would have vaporized the Earth's oceans. They would have sterilized the crust down to some depth. So this was not a trivial event. These were huge world-altering impact events at that time. The late heavy bombardment is also really important for understanding how Earth got its water. This is one of the kind of key ideas, is that, you know, Earth formed originally with less water, but because of impacts from either water-rich asteroids or comets coming from the Kuiper belt, these would have delivered later a large fraction of the water that makes up Earth's oceans. And so some of these models are known as the late veneer. The water delivered to Earth was part of a late veneer of organic molecules and water coming to the Earth from the outer solar system. So there's a lot of reasons that this is really important to understand its timing, how it happened, how extensive, all of those things. And we had gotten to the point, I won't say it was settled history or a settled story, but things were going pretty well. We had these dates of impact events, samples to date them, an understanding of the early impactor flux and dynamical models that explained that impactor flux. But then things started to get more complicated as we got more data. A lot of this data came from the Lunar Reconnaissance Orbiter, and a lot of it came from the Lunar Reconnaissance Orbiter Camera. Surprisingly, until LRO in 2000, when it launched in 2009, still in orbit today, there were fairly poor images of the moon. Some of them were quite high resolution, but they were not globally distributed. And even at low resolution, there were images that were kind of areas of the moon that you just couldn't see very well. The best images of the moon for looking at impact craters, morphology, a lot of them actually came from Lunar Orbiter, which was a pre-Apollo effort to map the moon. And that was done by taking Polaroid strips of images that were developed on the spacecraft and then scanned and relayed back to Earth. So pretty amazing way to do it, but still leaves something to be desired in terms of modern image quality. But so once we started getting that data back, we learned a number of things. A couple of them include just how extensive the effects of these large impact events are on the surface. This is the Oriental impact basin, which is on the western limb of the moon. Interestingly, telescopes mapped things, inverse. So it was Oriental because it was seen on the eastern side through telescopes. But when we mapped out the ejecta of this impact basin, really for the first time, this is from Meyer et al., saw these yellow deposits really streaking away from this impact basin, and they are really extensive, almost hemispherical. So realized these deposits of a single basin might be affecting a larger fraction of the moon's surface than we originally thought. Another kind of tie into that is that we got new images of the Apollo landing sites. This on the top right here is the Taurus-Littrow Valley. The Apollo 17 landing site was down here in this valley. And you can see Jack Schmidt sampling a boulder here. A lot of this material was originally thought to be Serenitatis impact material. This valley is right on the rim of the Serenitatis basin. And actually, there's still a big debate over whether it is. We don't know. But some of the new images show that this area, the whole surface of it is really littered with ejecta from the Imbrium basin impact event. And this rock here is the same rock here that Jack Schmidt was sampling. If you look closely, you can kind of see the multiple little pieces of it. And you can see the trail this rock boulder left as it rolled down the hill. So it rolled down this massif here. And so we think a lot of this material may actually have been from that superficial coating of Imbrium basin ejecta. And then we got some more samples delivered to us. We didn't have to go get them. And this is shown down here. This is in yellow, Apollo impactites. You can see this huge spike, that's that 3.9 late heavy bombardment spike. But when you look at some of these other sample classes, you don't really see that spike. The lunar meteorites, a lot of those were found. The first one was recognized in the 1980s, and then many, many more subsequently found in the Antarctic meteorite collection. Those are kind of spread across in age. Some of the little glass found in those are much more young. Typically, you can look at asteroid meteorites that preserve impact events, and those don't really show the same spike either. And if this was a solar system-wide event, you should see this in all those samples. So this left us with a big question. Do we know when the late heavy bombardment happened? And did the late heavy bombardment happen? Because there has been a kind of new idea. Well, it actually dates back quite some time, but new evidence to support this idea that even though we have sampled all these different areas on the moon's near side, maybe we have been going around collecting samples that are all dating the same event. Maybe that spike is all caused by the Imbrium impact event, which has really just profoundly affected the moon's near side. And if we don't have any constraints, that means we really, on the age of this, we really don't know what was happening in the early solar system anymore. Maybe we still had this cataclysm. Maybe we have dated different impact events. Or maybe there was, just various spikes that would have come from various kinds of asteroid disruption events. Maybe you had a smooth decline. I mean, we could come up with all kinds of scenarios once we lose our constraints on that early solar system history that come from dating the big impact events. So this is a big new problem. and how are we going to resolve it? One of the key ways is to just get very far away from Imbrium. We don't want to keep dating Imbrium. And so I've shown the moon here in a couple different ways. First, I've tipped it up a bit. The near side is up here. The south pole is down here. And this is showing thorium abundance. We think probably don't have time to get into all the really cool geochemistry of the moon, but thorium is a material that is prevalent on parts of the moon's near side and maybe something of a tracer of Imbrium impact ejecta. So get way down here by the South Pole. This happens to be where a lot of exploration will be focused in the coming years. We're getting far away from the effects of Imbrium here. And then looking at the moon's far side. Again, here's the South Pole. This is Aitken crater up here. And then the very creatively named basin, South Pole Aitken Basin, is about 2,500 kilometers in diameter. It is through kind of superposition relationships, clearly older than the Imbrium impact event, and it should have been substantially less affected by that younger impact event. So we would really like to know the age of this impact basin. It will tell us a lot about that early impact history, and it will kind of allow us to bookend. If this is the oldest, largest basin, this is going to tell us when the moon's record of impact events in the solar system, in the Earth-Moon system, when that starts. When did the moon's tape recorder turn on? So Artemis astronauts will be going to the South Pole. And at the South Pole, a lot of what they will be finding is broken up bits of rock. Unlike some of the younger landing sites in volcanic plains on the moon's near side, this is going to be a really ancient terrain, and it's been totally beat up. So a lot of the really important science is going to come from just collecting these kind of centimeter size little bits of rocks. These are from the Apollo 12 landing site, but we'll be raking through the lunar regolith, the lunar soil, and really trying to collect a very diverse sampling, and then getting kind of a statistical look of samples in the region, and looking at the geochemistry to kind of tie that in to find which pieces are dating that South Pole Aitken event. It's not going to be an easy task. So one of the things that we hope to do, and one of the things that was the highest priority for planetary science at the moon in that decadal survey that I mentioned, is a mission called Endurance. Endurance would be a rover that did a very, very long traverse over 1,000 kilometers through South Pole Aitken Basin. There were two ideas. You could do a totally robotic version of this, and that would be Endurance R. That's its traverse here. Endurance A stands for astronauts. So this robotic rover would start here, go down, and meet up at the Artemis base camp, collecting key samples from really specific locations throughout this basin. That'll give us an even better chance of dating it, of understanding how and when it formed, of maybe even finding some pieces of the moon's mantle, its interior, that have been exposed from this huge impact event.
How big is the distance on that, by the way? Because has there ever been a rover that's ever traveled that kind of a distance? I mean, that's
absolutely not. There has not been. This traverse, I think, is the pink one is about 1,800 kilometers.
wow.
And so, yeah, this would be a really ambitious mission, and it's taking advantage of a lot of the new technology that we have, particularly in terms of automation. It's not that hard to get a rover that can survive a long time and can travel long distances if you can really automate its driving, and it will be different than a Mars rover, which they travel on average so slowly because they're doing a different kind of science. They're looking at each individual rock. They spend forever staring at outcrops, but this would be a mission that would be planned out in advance, and you would go and you would scoop up different samples that have been pre-identified from our orbital images. There will be some technology development required to really get that automation to the place where it can pull this off, but it's actually a simpler problem than, driving your car down narrow streets in rush hour traffic. No other pedestrians to worry about. So that mission would end up at the Artemis Base Camp at the South Pole, and really kind of extend the reach of what the astronauts can do by going such great distances and bringing samples back to the astronauts. They can sift through them. They can bring back the most important ones. The other really important thing that will come from the Artemis mission, or one of the more important things that can contribute to this understanding of early solar system bombardment, actually comes from the moon's, just the environment at the South Pole. You saw the Earth kind of bobbing up and down there, upside down, and there goes the sun. The sun at the South Pole is always going to be on the horizon. It's going to make things challenging for the astronauts working in these strange lighting conditions, but that illumination provides a really important opportunity, because you can see areas, and even just in that little view, that are staying illuminated and areas that are staying dark. And now this is looking down at the South Pole, or a region right near the South Pole from above. And this is simulating illumination conditions that come from the topography, and then we've taken so many images near the South Pole that we can basically look at every single pixel and tell you if it is illuminated or not, and when it will be illuminated or not, and sum that up over many months and years. And then when you add that all together, you can get an illumination map like this one. This is just right near the pole. This is Shackleton crater. And this is showing in light and dark what fraction of time the surface is illuminated. So the brightest areas, very, very small ones, are illuminated large fractions of the year. Nothing is eternally illuminated, unfortunately, but you can get over 60, 70, 80% illumination. And then the dark areas never see sunlight for billions of years. And these are permanently shadowed regions. When we look at the temperature in these regions of the moon, this comes from the Diviner instrument on Lunar Reconnaissance Orbiter. It's a thermal radiometer. And we look at the temperatures. This map is showing the maximum annual surface temperature. So the very maximum temperature in these permanently shadowed regions is below 100 Kelvin. In some areas, it's down to 60 Kelvin maximum temperature. So some of the coldest places in the solar system are in these permanently shadowed regions. And they are so cold that any water molecules that were delivered by comets are hopping around the surface in these warmer areas. Anything that makes its way into these permanently shadowed regions is trapped, cold traps, volatile traps, and will stay there for essentially, for all intents and purposes, forever. And so a huge thing that the Lunar Reconnaissance Orbiter and multiple missions have worked on now over the past 15 or so years is understanding how much water is in these permanently shadowed regions, How is it distributed? And then the big open question that we have no answer to yet is how did it get there? But we do have evidence now from neutron spectrometer showing where there's suppressed neutrons that's due to hydrogen and presumably water. We have seen some reflectance spectra. If you average them up over enough time, you're getting enough photons reflected that you see some evidence for water ice in those kind of patchy blue dots. And there was the L-Cross mission. NASA slammed a upper stage of a Centaur rocket into Cabeus crater, one of these permanently shadowed regions, looked at the ejecta of the crater that impactor made and found that it had about 5% water in its ejecta. So we know there is some ice, we know there is some water. And one mission I will note, because it just arrived at the moon this week, is the Danuri orbiter. That's South Korea's first mission to the moon. And there is a NASA instrument on there called ShadowCam that will map the permanently shadowed regions using the very few amount of photons that make it in there bouncing off nearby illuminated terrain. We'll map those at just under 2 meters per pixel, so get really incredible images in there. Even still though, there are so many questions about how much water is there. Can the astronauts, drink it? Can we split it apart, use it as rocket fuel to venture out further in the solar system? Can it be a resource? The part that I really care about is where did this water come from? We have no information about that yet. One of the ways that you can understand this is looking at the isotopic signatures, the hydrogen isotopes, the D to H ratio, and also looking at oxygen isotopes. Just showing hydrogen here because it can point to specific kind of outer solar system comet origin, or more water-rich asteroid origin. And so it'll be key to get onto the surface, bring a mass spectrometer with you. And these are some of the proposed Artemis landing sites. So the astronauts for Artemis 3 haven't kind of long story, but we don't know what instruments they'll bring along with them yet, but presumably one of them will be a mass spectrometer that can help us tell the origin of this water. This is an example of one of the coolest landing sites, the one I hope that they go to. This is a connecting ridge between Shackleton crater right at the South Pole and De Gerlache crater. This is about a 30-kilometer distance. Both of these and some of these areas are all permanently shadowed regions. The astronauts are not going in there. It is very cold, as we discussed, and they're not going to go in there, but they can set up instrumentation. And there are many smaller permanently shadowed regions that they can sample. Artemis 3, the astronauts are only expected to go about 2 kilometers from the lander. And so really it's going to take a lot of exploration returning to understand this problem. And that's why I emphasized the sustained lunar exploration, because this isn't going to be answered in a single mission. Part of that is just because it's so ancient. We don't think that, there's beautiful preserved ice skating rinks of ice in these areas. They've been beat up for billions of years, and the distribution of the ice is probably pretty patchy. But we do hope we'll get some samples back. It will not happen on the first crewed Artemis mission because they will not have a freezer. We'll get some information, but they'll not be returning samples at cryogenic temperatures. So that we'll have to wait for that kind of development in future missions. But one of the upcoming missions is going to be Viper. This is a rover that is going to land in late 2024. It's about a 100-day mission, and it's going to traverse 20 kilometers. This is kind of the potential mapped out traverse right now. And it's going to an area near Nobile crater. In a second, you'll see the permanently shadowed regions are going to show up mapped here. So the black areas are kind of temporarily shadowed regions. The blue are the areas that you never see sunlight. And you can see that the Viper mission is kind of a first look. It's a solar powered rover, so it can't spend too long in these shadows. And it's really just like dipping a toe into some of these permanently shadowed regions. It'll give us a lot of really cool information. It's going to give us some of that isotopic information to get at origin. But because it's not going really deep into these permanently shadowed regions, it's really a first step. And some of us have mapped out, similar to the Endurance mission I talked about. All right, what if we could do a really great, nuclear powered rover, spend a lot of time in these very cold areas? That's when you're really going to, that's where you're really going to get some great information. So that is for the future, not currently yet planned, but would be great. I'll just briefly mention too, a lot of the upcoming work, upcoming landers they're going to be done through this Commercial Lunar Payload Services program. This is a program where kind of like, delivering supplies and now astronauts to the International Space Station. NASA is going to be buying a delivery service from these commercial providers. They will, they basically charge per kilogram. So you pay by the kilogram to deliver your payload to the moon. The Viper mission is going to be delivered by one of these commercial landers. It's the first really big mission that will go. It's going to be delivered by an astrobotic lander. Intuitive Machines has several landers already under contract with NASA, as does Firefly. And I will note that none of them have landed yet. It's quite easy to find very beautiful renderings, as you see here, of all of these landers, but finding pictures of the actual built hardware is a little bit few and far between, but it is coming. This is a really impressive map of all the deliveries that are currently planned from these commercial landers between 2023 and 2026. Some of these will probably get delayed a bit, of course, but the first one is scheduled to be really just a few months away, the first quarter, March of 2023, and that's going to be this Intuitive Machines lander near the South Pole. You can see a bunch of these landing near the South Pole, including the Viper mission we talked about. And then others that are going to sites of scientific interest. The two that I am working on, one will be going to Reiner Gamma, a really weird feature where we hope to learn about how this moon surface is affected by space weathering, the solar wind, micrometeoroid bombardment. And then another that will be landing on top of a silicic volcano, trying to understand how the moon got its weird volcanic, evolved volcanic compositions. So this is a really exciting prospect. Some of these landers, they're doing kind of minimal science, and then they're bringing along a host of other weird stuff, like, they'll be taking pictures and selling them as NFTs. They'll be bringing ashes. I mean, it's a commercial. They're selling space to whoever wants to buy it for the most part. And one of these companies has already gone out of business, unfortunately, Maston. So I had always worried about these first landers, will they make it will they crash on the moon? I hadn't actually thought that much about the fact that some of them might fail before they even, take off. But we will, this is part of this lunar economy that NASA has committed to investing in and helping to build up. Not all the companies will make it. I'm just want to include this chart because it's just really crazy, the overall plans for everything that NASA has going on at the moon in the coming years. Really, these are the only dates, these first up through 2025, that have been planned out in a lot of detail, but wow, there's a lot going on, and really ambitious program that will continue out into the later parts of the decade. We'll see how the details shift as that goes along, but going into Artemis 4, 5, 6, very exciting to see. And I see a hand raised, which is good timing because I will leave it here at a view that hopefully some of these astronauts and the robotic landers will be looking at our beautiful home planet from the surface of the moon. All right, and happy to take any questions.
We have a couple. One of our members, Bob Tobin, had asked, "Where's the HLS lander?"
Where will it land, or?
I didn't see it on your list. Did I miss that?
Oh yeah. Do you mean in this one? This
Yep.
list? Yeah. So this is only showing the CLIPS landers. HLS, the Human Landing Service, that is the first one that is under contract is, of course, the SpaceX Starship. And that's going to land near the South Pole. TBD on where. That was this kind of range of different sites that have been proposed so far. But yeah, that one is that one's kind of in a class of its own. It's not on the map with all the little small ones.
He also asked, why not use Starship on the other programs as well, just to get the stuff there. Obviously,
Yeah.
Starship is a great way of moving a lot of hardware in a quick hurry.
Yeah, absolutely. So Starship actually is, SpaceX is part of the CLIPS program. They could bid on some of these deliveries. So far, NASA has been asking for smaller deliveries, like in the 50, 100, 200 kilogram range. And that is just, Starship its capabilities are like way higher, 100 metric tons eventually down to the lunar surface. So yeah, I mean, they could bid on one of these. They just have an enormous vehicle. I do think that as we move forward, hopefully NASA will begin really taking advantage of the huge capability that lander brings, as well as some of the other upcoming HLS landers. The proposals for a second lander just went in, and a second company will be selected too.
Bezos, probably.
So SpaceX is already under contract for Artemis 3 and 4. The others that went in, one was led by Blue Origin, one I think was led by,
I think Boeing had one too, I think.
Yeah, they partnered in with Blue Origin, I believe, or with, I don't know. It's kind of like a big amalgamation of all the different companies, and they're split into two groups.
Actually, I had a question here too. Is there any resource that gives information on how these startups find about the NASA and other space contracts and apply so that they could possibly become a vendor themselves?
Yeah, well, there's a great a consortium that actually where I work, APL, helps run, called the Lunar Surface Innovation Consortium. And that is a really great place where all the CLIPS vendors are involved, the technology development, a lot of the discussions on, what are the current NASA technology needs, what are the calls for proposals. There's a lot of information that's available through that.
I'm sorry I missed Labkoff. He had his hand up. So Stephen Labkoff, you had a question you want to ask?
Yeah, I do. Thanks, Stan. And what a great talk. That was
Yeah,
just really
interesting.
wonderful.
Thank you.
It's been years, when I was a little boy when all this stuff was going on in the first place. And it was one of the things that got me interested in science and led me eventually into medicine, unfortunately not astrophysics. But this has been wonderful. I have a question kind of a political nature. As we get more and more efforts to get back to the moon, nobody really owns the moon at the moment. What happens when that starts to become an issue? Is that something you guys even think about in terms of, like, if we land somewhere, it's not our place, it's still a universal entity. Are we going to start staking out claims to parts of the moon where we land and start working?
Yeah, that is a really important question. And I'll just note that the first bit that you said, that you got interested in, science because of lunar exploration, that's really common for so many STEM people, even if they didn't end up studying the moon specifically. But yeah, a lot of people think a lot about this. That is part of what the Artemis Accords are working to do, kind of build up a big international group that have all agreed to play by the same rules. And no one can own different terrain on the moon. But I think the kind of model that we're hoping to work toward is like McMurdo Station in Antarctica. So that is, international terrain, but there's a huge science outpost built up there. Many countries contribute to sustaining it. A lot of fantastic science happens from there, but it's not, one country's territory. But yeah, if you are interested in more of the policy aspects of that, you can send me an email and I can point you to some interesting references.
Thanks so much. I'm curious about it. I don't know that I have anything to contribute to the conversation, but I am curious as to what happens when people start fighting about this, because it's inevitable.
The from the Earth to the moon scenario, where we're fighting with the Russians at Shackleton, and now the Russians may not be there, it may be the Chinese, and so it is a political thing, and how we deal with somebody popping a flag up there and saying, well, it's ours now, and it may happen. It may be a corporation that does it instead of a country.
Yeah.
Yeah.
Oh, go ahead.
Point. No, I said I hadn't thought about that, Dan, but it's a very good point.
I have a question. Does NASA have any timeline as to when they think they will be able to use the water on the moon?
When they will be able to use it. Yeah, so the first, okay, there are many steps to this. First is kind of proving out how much water is there. If we don't, and where it is, because, right, is it buried? How far below the surface is some of it buried? What form is it in? Is it just kind of little tiny pore space filling water, or is it in bigger chunks? And how accessible is it? Shackleton is a hugely deep crater. Is it only in the bottom of that? So that's what Viper is the start of, is basically a resource campaign. And the terrestrial geologists talk a lot about reserves, a resource versus a reserve. It has to be present in enough quantity, and all of those things have to add up so that it makes economic sense for you to be able to use it. And we're still at the point of proving out if it is going to ever make economic sense to be able to mine that water. And I think there's, a lot of optimism there. But first, we're doing that. Second step is basically the in situ resource utilization pilot demonstration, bringing up the infrastructure you would need to mine the water in smaller quantities, convert it into a usable form, separate it out from all the dirt, and then scaling up from there. So that is definitely a long-term plan, I would say, into optimistically early 2030s is my guess. I mean, I think some people think you could do it sooner, but I do not think it will happen sooner.
That's yeah. So another thing, kind of back to the commercial, I wanted to ask you about too. So as they start mining the water, they start converting the water into usable energy. Are there other resources on the moon that are useful, like hydrogen-3? Is that the next kind of step? Is that where they start mining that and then creating massive dust clouds on the moon? Does that happen next too?
Well, luckily, without an atmosphere, things settle down pretty quickly. But yes, no, your real point is a good one. And yeah, it's all the same question of, once you have enough infrastructure built up at the moon, so that you're not doing everything as a one-off mission, that's when you can start really looking at being able to utilize the moon's resources. And just the rocks themselves are a resource. You can melt them, you can get oxygen out of the rocks, you can get iron. Yes, there's various implanted solar wind gases that could be mined. There's water in some of the volcanic deposits, not here at the South Pole, but in areas like the Aristarchus Plateau, big volcanic glassy deposits that are thought to have water. So there's all kinds of things you can do. And actually, I think many are working on technologies that actually will try to extract oxygen from the soil. And people think that will happen before you're able to actually start mining the water. So if you wanted to use oxygen, life support, but also then you only have to bring up half of your rocket fuel, the hydrogen part. So yeah, there's a lot to do, and it'll take a lot of technology development and really that infrastructure build up on the moon.
You've traveled around the planet looking at craters, and obviously you have a lot of interest in geology. If given the chance, would you go to the moon to go and poke around and see it up close and personal?
Yeah, I think someone just asked me this the other day, and I mean, maybe when my kids are older.
Right. Yeah.
Like, I have enough trouble like
Hopefully they'll still be asking for hugs
days.
then too, though. Hopefully you'll still get hugs, before you get on that one.
Yeah.
I read that you went to Northwestern, which is not exactly a school that's known for its planetary sciences. What when you went there, was your idea to be an astronomer, or did you kind of lean towards something else?
Yeah, you're right. Northwestern is not known for that. I went to school having no real clue what I wanted to do. I did spend some time in the astronomy and physics department. Did not love it. So I was lucky that at the time when I was there, there was one person in the geology department named Mark Robinson, who I still work with today. He is the principal investigator of the Lunar Reconnaissance Orbiter Camera. He happened to be there because of a two-body problem thing. And I just kind of stumbled across his work, got a summer job with him, and thought I was actually looking at pictures of the asteroid Eros all day. There was the ongoing NEAR mission back then. And yeah, and then I was hooked.
Yeah, the moon is a great gateway drug. I think that, it's something that all of our ancestors for all of time have looked at and go, wow, that thing's kind of cool. I wonder what that is, and make up their stories about it. And people have dreamed about it. And now that, 50 years later, we're going back there again, and that we're we're actually getting up close and personal with it is, I think it's so exciting. And it is such a great way to kind of introduce people to, you know, basic observational astronomy. I think it's the first thing that everybody always wants to look at. And yeah, I mean, I'm hooked. I love this talk today. I like hearing about what we're going to do and how we're going to do it. I think it's just fascinating.
Hey, Dan, I got one other question, and it's this. So on our webcast that we have here tonight, you know, we have people of all ages, and some of those people are young people who are not quite in college or graduate school yet. You know, as I was coming up through my development, it never really was an option to get really deep into astrophysics or get into something that would take me into this trajectory for a whole host of reasons. But people today have a lot more optionality. What would your recommendation be to some of the younger listeners who are on the call tonight who might really want to follow in your footsteps and get into this? How would they go about it? Who would they call? Where would they go to get their first taste of all this in like real life, an internship or something like that? What are your recommendations?
Yeah, there are so many ways to get involved. I mean, at Johns Hopkins Applied Physics Lab, we have high school internships. We work with high school kids who come in and, you know, spend like 10 hours a week or some time in the summer. NASA has high school internships. I mean, I love the geology and that is my thing, but, you know, there's a ton of different types of science. I work with, you know, physicists, people who study the sun, but a lot of that is, you know, you can do interesting stuff to study the sun from the moon. And then, of course, engineering, all kinds of engineering. Now there are a whole bunch of, you know, MBAs and tech startup people working at the moon. And then one of the things that I'm always really jealous of is all of the people at NASA, at APL, JPL, all over, who do the art. I mean, even just looking at this image here are some of the different visualizations that we saw. You know, you're taking this kind of science visualization, but sometimes there's just pure art, graphic design, and they come up with really beautiful things. So NASA has incredible artists, and they have communications specialists to help share all of the work and the kind of boring technical language, turn it into something a little more accessible. I don't know. Yeah, I mean, for me, it was just finding someone who was doing this and actually seeing what they were up to, because then you realize, like, it's just, you know, oh, it's just people. I could do this too. It's not that hard.
Well, it's certainly inspiring. I get excited about talking about this stuff all the time, and we all really appreciate you spending some time with us tonight as we get ready for the holidays here. It's just been it's crazy to think about all this stuff, and thank you for your time today.
Oh yeah,
So,
absolute pleasure. Yeah.
well, let's stick a fork in it then, and we'll be back again next month. I guess we're going to have public night tomorrow night, so if you'd like to come out and look at the sky, well, that's what we'll be doing after 8 o'clock tomorrow. And I guess that's kind of about it for tonight. We'll wish you all a very, very happy holiday, and we'll see you all next month. Thank you, everybody.
Thank you. Thank you very much.
Thanks, everyone.
Thank you.
Talk. Great program tonight. Thanks.